Hello. Yeah. So can I start? Yes. Okay. So very good morning to all of you. So thank you very much for inviting me for this today's program symposium. So and I'm happy to talk in front of my guru, my mentor, Dr. Kailash, who has guided me throughout my career, and also some of the work that I'm going to show you. And it is the main ideas are given by Dr. Kailash, and still we are collaborating with in his guidance. So I'll discuss about the recent activities that we are doing using the stable weekly bound projectiles mainly from Peloton Linac facility at Mumbai. So I will take a tour of the different aspects that we are doing with stable weekly bound projectiles, and then I will summarize. So okay, so these are the two talks. Previously, I have given invited talks. So the 2012, I have given my University of Holwa. I was a postdoc. So that time I had the first exposure of the silicon strip detectors. So which we are now regularly using. Like 2014, I came back, and from 2014 onwards, we have built this silicon strip detector array. So that was the first training I got from this place. We have used several kinds of silicon strip detectors in different configurations. We also done the pulse chip analysis studies. So we are using that kind of all the expertise that I have gained in the postdoc, that I am using it right now in our facility. And the 2019 I gave the second talk, the innovative talk. That time I talked about our review article in physics reports. So it was about the systematics of incomplete fusion using strongly bound and weakly bound projectiles. So I am going to also show some of the results from this talk also. Okay, so the outline of my talk will be, I will discuss about the what is weakly bound nuclei, the role of low separation energies, and the cluster structure. Then the recent studies that we have carried out with weakly bound projectiles, mainly the fusion cross sections, the alpha production, breakup, transfer, and elasticity using Peloton Linac facility at Mumbai. And then I'll also in between I'll talk about the systematics of various reaction channels that we have come up, and finally summarize. So what is weakly bound nuclei? So weakly bound nuclei are this kind of there is the ground state is very close to there are one or two bound states, and the continuum, which is the resonant states, are very close to the ground state. So whether there is any effect of this continuum on the reaction mechanism that we study. In the case of tightly bound nuclei, as you know, there are some bound states, few bound states, and the continuum is above 8 MV. So that kind of difference is there between tightly bound and weakly bound nuclei. Also, there is it is having a cluster structure, the typically alpha plus X kind of cluster structure. So some of the nuclei are listed here. So like lithium 6, lithium 7, and beryllium 9 are the weakly bound stable nuclei. They are having the cluster structure of alpha plus T, and 8 beryllium plus neutron. And this is not working. Some pointer. Okay, so the typically alpha plus X kind of cluster structure, and the separation energies are from around 1 to 2 MeV are the separation energies. And in the pink, they are shown as the radioactive nuclei, the weakly bound unstable nuclei like helium 6, beryllium 7, helium lithium, and helium beryllium. They are also having the cluster structure and also the weak binding energy. So this is typical characteristics of the weakly bound nuclei. They are having the alpha plus X kind of cluster structure and the weakly bound, the low separation energy. So typically also the tightly bound nuclei also have the alpha clustering. Like you can see, the carbon 12 has the 3 alpha cluster structure, oxygen 16 has 4 alpha cluster structure, or neon 20 has the 5 alpha cluster structure. So alpha clustering is a kind of normal phenomena in the light nuclei, and we are actually working on, we are trying to find out the role of this alpha clustering in the reaction mechanism. So when you go away from the Reynolds stability, we have the weakly bound unstable nuclei like helium 6 or helium lithium. So they have the complex structure, we can call it Borromean structure, where the helium 6 is composed of alpha plus neutron, or helium lithium can be considered as 9 lithium plus neutron. So they are also having the low separation energies, only around 1 MeV kind of separation energies, and exotic shapes like this kind of ring configuration, entangled ring configuration. They have extended density distributions and large probability of the valence neutron, which is bound out in the outer shell. So these are the nuclei which are produced in the radioactive ion beam facilities. Okay, which is the whole world is trying to populate this kind of nuclei and accelerate this kind of nuclei. So in the meantime, we have these stable ion beam facilities in our country. We are trying to utilize these facilities, and we are doing the similar kind of studies that is possible with the radioactive ion beams. So you can consider this helium lithium, the structure of helium lithium is similar to the size of the lead nucleus. This is well known. So what is the advantage of using stable weakly bound projectiles? It is having the high beam intensity. So good beam quality is possible, and it is like a better foundation for studies with RI beams. So we are trying to make this whatever available resources we have in our country, we are trying to utilize it and study the similar kind of reactions that is possible with the radioactive ion beams. So what are the reactions that we are studying? So we are doing the elastic scattering measurements. So weakly bound projectile which interact with the target, it can scatter elastically, or it can transfer few of the nucleons, that is called few nucleon transfer, or it can break up in the field of the nucleus. So we can detect the non-capture breakup. Suppose lithium 7 is there, it can break into alpha and triton. We can measure this alpha and triton in the coincidence. Or there is a possibility of breakup fusion. So it can, one of the fragment can break and it will fuse with the target. It is called as incomplete fusion. Or it is possibility of transfer of followed by breakup. So transfer of one nucleon and then the remaining nucleus will get it will break up. And also there is a full possibility of complete fusion. So we are studying all these kind of reactions in our studies, and we are trying to find out the role of cluster structure and weak binding on reaction dynamics. Study of breakup and transfer breakup reactions and the relative importance in these studies, and validation of available theoretical models. So this is the facility that we are using, BRC TFR electron linear facility. It is started in 1988, so it is like 37-year-old, or rather you can say young machine, which is delivering beams of various kinds. Mainly, we are utilizing mainly lithium 6-7 and beryllium 9. And this is the main features are available on our TFR website, tfr.res.in/pel. And this is the typical structure of the machine. So ion source is situated at the top of the accelerator tank, and the terminal is in between the accelerator tank. And then we have two beam halls, cascade beam hall is the old beam hall, and the new superconducting linear booster, where we can accelerate the beams from the peloton. So So now you can also see the various kinds of BRC newsletter has published recently to May, June 2025, and in this newsletter we have highlighted all the work that has been done over the last few decades from this facility. So one can have a look at this newsletter to find the more updates on the recent work. So these are the pictures from the electron beam hall, the old beam hall. We can see various beam lines, scattering chamber, and the irradiation facilities, and the atomic physics facilities people are using. And then the linear beam halls, hall 1 and hall 2, where different facilities are there. People are aware. The younger audience maybe have not seen it, so I'm purposefully showing it for them, so we can visit the facility and perform the experiments. So these are the typical experimental setups that we have. So like I was telling about the silicon strip detector setup. So we are having several silicon strip detectors. We can arrange in different configurations and do the full angular distribution studies. Like I shown here, the silicon strip detectors are arranged in one, like it is covering 90-degree coverage. So we can do the full 180-degree coverage by moving this arm. And it depends on the purpose of the experiment. We can mount in different configurations. Like you can see here, there are 3 setups showing 3 different configurations. Then we have the charge particle array, the full 4-pi detection of the charge particles can be done. We have the fission fragments, mass distribution studies from the MWPCs we can do. We have the offline gamma counting setup, where we can do the offline gamma counting. Then we have the flower detectors, where we can use the full INGA array, or we can use part of the detectors for doing the online studies. We have neutron detectors also, in different configurations are used, and neutrons in coincidence with charge particles also is performed in this kind of setup. This is neutron wall, and this is barium fluoride array. So we have different kinds of setup, and as per our requirement, we can set up this, use these facilities. Okay, so today I am going to talk about the recent studies that we have done using lithium 6-7 and beryllium 9 beams using BRC TFR facility. lithium-67 beams are regularly available at our facilities, but beryllium-9 is very complex kind of beam, and we need safety permissions from different safety requirements are there. But I am thankful to the my seniors for getting these permissions from the safety, and we could have these 3 campaigns of beryllium-9 in 2010, 2018, and 2023. And we have done a lot of experiments with beryllium-9 beam, and I am going to show some of the results on different topics. Okay, so I will first I'll talk about diffusion cross sections that we have done using the online and offline gamma ray measurements. Now we have done a lot of systems using lithium-67 and beryllium-9. As you can see here, this is the full complete list of the data that we have done at our facility, and also some of the boron-10, boron-11, and some of the tightly bound nuclei. So here we use the 2 techniques. One is the online gamma ray measurement, and second is the offline gamma ray measurement. So online gamma ray measurement, when the evaporation residue is a stable nucleus, we can measure the gamma ray de-excitations, like here A plus B forming compound nucleus C. It can decay by different residues, and we can detect these different excitations from the gamma ray de-excitations from the excited states of the residue. Or in the offline gamma ray technique, when the residue is unstable nucleus, we can measure the gamma rays after beta decay or electron capture. So these 2 techniques can be combinedly used and for getting the cross sections. So this is the first few experiments that we have done using the Clover detectors when I was a postdoc with Dr. Palit, and we have designed this chamber also to accommodate the charge particle detectors. So the charge particle detectors are placed at some certain angles, and the 2 Clover detectors are used in this configuration. And we are measuring the gamma rays from this. And similarly, offline setup, we have the dedicated setup at Peloton facility that is 30° north beam line, where we can irradiate the sample in this particular beam line, and after certain irradiation time, we can take out the sample, and we can count it in front of the outside the offline for the offline gamma counting. So this is the by using the both online and offline gamma ray technique, we can identify the different residues and finally get the cross sections. And also we have used the INGA array, full INGA array with 17 clovers and compact digital electronics, and along with that few of the detectors in the certain angles for certain studies, particle gamma coincidence, we have used this kind of setup also. So this was the first experiment using beryllium-9 plus tin. Reaction was in the first campaign at TFR. So we could see this particle spectrum, very beautiful particle spectrum, where the alpha band is shown here and the beryllium-9. And this is the gamma ray spectra with Clover detector placed at certain angle. We could able to identify different residues populated in this reaction, and we could identify these residues. So thanks to the nuclear structure community who are helping us to know the gamma lines. So once the experiment is performed, we can identify what are the gamma lines populated in this reaction. So generally we are interested in the low lying transitions. So this is the typical scheme for the beryllium-9 plus tin forming 133 xenon, and it is decaying into 3 residues. So we can list the gamma rays which are possible, low energy gamma transitions which are required for our analysis, that we could identify from this particular level scheme. So this is shown here. So typically for even residues, typically what we plot is the gamma ray cascade to see the population at z equal to 0. So we can extend it up to z equal to 0, and that can be assigned to the residue cross sections. But for the ordered nuclei, we have to add all the gamma ray transitions which are populating the ground state. So this is what we are doing for the even and odd nuclei. So there is some limitation. So what about the feeding directly to the ground state? So that part is missing. So that limitation is there of the online gamma ray counting. But best solution is if you can measure the offline gamma ray measurements, then we can combine these 2 measurements and validate whether whatever you have measured in the online, whether it is accurate enough to consider as a residue cross sections. So we have used both the techniques, and in this particular case only gamma rays were available in the online measurement. So we have plotted the excitation function of different residues, and it is shown here. And once you add this the residue cross sections, we can get the complete fusion cross sections, which is shown here. So this is the fusion cross section as a function of center of mass energy. And what we can see is that at above the barrier energies, there is separation compared to the model calculations. That is called one-dimensional barrier penetration model, or the coupled channel calculations. So we can see some kind of separation with some factor, it will be able to reproduce the data. So that is called suppression in the cross sections at above the barrier energies. Okay, next we have used the same target and bombarded lithium-7 and lithium-6 for the same target, same setup in the next experiments. So we have populated this 131 iodine, the compound nucleus, and we have seen the de-excitations from these iodine isotopes. Similarly, 6 lithium plus 114, we populate this 130 iodine, and we can identify the residues, gamma lines, from this online gamma ray spectrum. So we could able to identify all these lines from these different residues. And this is the offline measurement. In this particular case, offline measurement also is possible. The same nuclei can beta decay, and we can measure the de-excitations after the beta decay. So we can see the offline gamma ray spectrum from this reaction. We could able to identify all the residues, and these are the typical half-lives and the gamma ray energies, and the branching is shown here. And we could able to verify the half-lives from this half-life plot. So this is the final picture where we can show that the online data and offline data are nicely agreement with each other. So that confirms that the whatever we have measured online, it is perfectly fine. And similarly, 3N and 5N we can able to see here. And it is in agreement with the statistical model calculations. So it shows that it is coming from the compound nucleus. Okay, so this is how we can get the fusion cross sections after adding all these residue cross sections. Similarly, for lithium-6 is shown here. Okay, so now lithium-7 plus 10 is also showing same kind of separation at above barrier energies. So lithium-7 plus 10 and lithium-6 plus 10 also showing separation at above barrier energies by certain factor. Okay, so I will show you the total picture in the next slide. And this is the comparison between lithium-6 and lithium-7 at different same E by VB. You can see that above barrier energies 6 lithium is slightly separates compared to the lithium-7. Okay, now this is the incomplete fusion cross sections where we have plotted is the D-capture cross section, deuteron capture and alpha capture. So what we can see here in the lithium-6, deuteron capture is much more than the alpha capture, and similarly in lithium-7 we have the tritron capture is much more than the alpha capture. And this feature is almost similar in all the studies that we have been carried out using lithium-6 and lithium-7. That tritron capture is dominant in the lithium-7 plus lithium-7 induced reactions, and deuteron capture is dominant in the case of lithium-6 induced reactions. Okay, now what we have plotted is the systematics of CF suppression factor. Is the suppression factor which was shown as the suppression at the above barrier energies is plotted as a function of ZP, ZT. So here different projectiles are considered here: lithium-6, lithium-7, beryllium-9, boron-10, and boron-11. What we can see is that for all the targets, the suppression factor is more or less constant for a particular projectile. So if you take the case of lithium-6 is typically 0.65 is the suppression factor. In the case of lithium-7, it is around 0.75 the suppression factor, and for beryllium-9 it is 0.7 is the suppression factor. So, and there are some exceptions like this. I will talk about this later. So once we plot this FICF, that is 1 minus FCF suppression, that is if you take this as a constant 0.7, 0.75 like that, and we can plot as a function of alpha suppression energies, what we can see is that there is a tendency of showing some kind of exponential behavior. We have plotted for all the weakly bound nuclei, and also we have combined the strongly bound projectiles. So it is showing some kind of exponential behavior as a function of alpha suppression energies. So alpha clustering is playing a role in this kind of studies in the CF separations. Okay, we have also plotted the systematics of CF and ICF cross sections available with lithium-7 projectile on different targets, and it is some kind of showing some kind of universal pattern for the complete fusion, tritron capture, alpha capture, the total ICF and total fusion. So this kind of feature systematic studies that we have been carrying out so to understand typically the lithium-7 induced reactions or weakly bound nuclei. Now, we have also changed this anomaly, what is there in the samarium target. So, as you can see, samarium is not following this kind of systematics, okay? Samarium is showing only 10% separation. So, we have looked at the data, what is wrong with that data. What we found that they have measured, the Gomez et al., they have measured this by using X-ray, offline X-ray measurement. And if you see the spectra here, they have used some kind of multi-Gaussian fitting to get the yields of these residues. So this is making some kind of like problems in the extraction of the yield. So we have done it by the gamma ray counting. So in the recent 2023 campaign, we have used the non-beryllium beam on 144 samarium, and we have identified all the residues from the complete fusion and incomplete fusion, and they are having very good half-lives range in the range of measurement, so from few hours to few minutes, and also it has granddaughters. We can confirm daughter and granddaughter both. So this is typical gamma ray spectra that is possible from this reaction, and we have identified all the residues, and we have plotted the residue cross sections, and finally we can get the fusion cross sections. So here we can see that it is suppressed by 0.7, which is in agreement with the totally available data. So this anomaly we could able to resolve by our latest measurement from the gamma ray counting, and we are yet to publish this result, and hopefully we will publish it very soon. Now I come to the second topic of alpha production. So alpha produces the lithium-7, the weakly bound nucleus interacting with the target. It can produce the alpha in various ways. So it can produce by non-capture breakup. Alpha can break in the field of the target, and none of them will be captured. So that is called non-capture breakup. Or it can ICF or transfer. So the fragment will fuse with the target, or it can transfer to the target, and alpha is the outgoing channel. So we can get the alpha as the outgoing channel in both the cases. Or the compound nuclear decay. If the residue is alpha active, the alpha aberration also is possible from the compound nucleus. So this is this typical plot what we can get. Lithium 6 plus this much, we can get the lithium elastic band and alpha, very nice alpha band, and this is the alpha energy spectra, which is showing the peak at 4/6 of the beam energy, and we can get the angular distributions from this, and which is peaking at varying angles. Okay, thank you. So what we have plotted here is the whatever data we have collected using the lithium 6, lithium 7, and beryllium 9. We have plotted as a function of E by VB. So as a function of, this is the sigma alpha inclusive cross sections. What is shown here is that it is also showing that some kind of universal behavior. So lithium 6 is behaving universally for all the targets. Similarly for lithium 7 and beryllium 9. So it depends on the separation energy of the projectile, how much the alpha production is more. So alpha production is more with lithium 6 and similarly with beryllium 9 than 7 lithium. 7 lithium is having the separation energy of 2.5 MeV, and 6 lithium is around 1.4, and beryllium 9 is around 1.5. So beryllium 9 and lithium 6 are behaving similarly than lithium 7. And the part of this alpha production is going into the reaction cross section. So this is plotted in some different plots. So we are comparing all the weakly bound projectiles and radioactive ion beams in the one plot. What we can see here is that radioactive ion beam is like only data is available with helium 6 and few points on 7 beryllium. We can see that radioactive ion beams like helium 6 is following some kind of one behavior, which is much more than the weakly bound projectiles, than the like lithium 7 is having different band, and lithium 6 and beryllium 9 are following some other band. So also we have compared with the tightly bound nuclei. So tightly bound nuclei, there are a lot of data available. So we have plotted here also. So what we can see here, the alpha production with radioactive ion beams is much more than the weakly bound projectiles, and is followed by the strongly bound projectiles. So this is the plot which is shown as a function of alpha separation energies as a function of sigma alpha. So what is plotted here is around 1.1 VB. We are taking the data of different targets. And this is lithium 6, helium 6 are plotted here, and all the projectiles, and it is showing some kind of behavior as a function of this kind of expression we could able to fit, except these beta points of beryllium 9 and 7 beryllium, and we are trying to investigate why it is not following with 7 beryllium and 9 beryllium. So this is detailed investigation of alpha production was done in the two publications of lithium 6 plus terbium and 7 lithium plus niobium. So what is shown here, lithium 6 plus terbium, the alpha cross sections are almost equal to the, it is not able to reproduce only by using decapture. So one neutron stripping also is required to get this cross section, to understand the alpha production cross sections. But in the case of lithium 7, the T-capture is dominant reaction mechanism, which is almost close to the reaction cross sections. That is what is plotted here. Next, we have done also the particle gamma coincidence measurement to understand the process of transfer breakup and the direct clusters transfer. So we have done using this Inga array, and along with the particle detectors, we could able to do this experiment. And what is shown here is the particle gamma coincidence. This is the gamma lines, and this is the alpha band. So when we put the alpha gate on the gamma band, we could able to see the residues populated in the 96 molybdenum, which is directly from the triton transfer. So triton transfer residues are seen here, the gamma lines are seen here in this plot, which is the direct signature of the T cluster transfer from this particular measurement. And the remaining residues are coming from the either 1 neutron transfer and 1 neutron evaporation and 2 neutron evaporation. Then we have the breakup cross-section measurements that we are doing regularly by using our silicon strip detectors. We have 16 strips and 16 strips x direction, 16 strips in the y direction. So we can do the pixel kind of measurements, and we can do the breakup studies. We can find out the relative angle and relative energies, and we can identify different configurations. Like is shown here, direct breakup, resonant breakup, or transfer breakup, we could be able to identify from these kind of plots, Q value versus relative. And these are the studies that have been carried out using 6L lithium beam and beryllium-9 beams at our facility. So one example is shown here, energy correlated spectra, lithium-7, the different bands, direct breakup can be identified by using the relative spectra. Yes, I'm about to wind up. So, and similarly, 1 neutron stripping followed by breakup, and 1 neutron pickup followed by breakup is seen. So it is, all these things can be identified by our very nice setup. So these are the spectra, angular distributions that have been measured using this setup, and we could able to get the non-capture breakup and transfer breakup cross sections. And we have, this is the summary of all the data that is available using lithium-6 and lithium-7 beams. In our review article, we have published this. And what we've seen here, the non-capture breakup is only contributing around 10 to 20% of the 20 to 30% around of the increased alpha cross sections. So non-capture breakup is not the dominant part of the alpha production, but is something else. So here is the complete picture of the increased alpha cross sections. The major part is from the triton capture in the case of lithium-7, and in the lithium-6 it is the neutron capture is the dominant part, as shown in these two publications. And the remaining part is very small compared to the these transfer cross sections. This is the recently there is a development I am about to complete. IOE models where it is developed by Lee and Morrow, where they could able to understand the alpha production by using these elastic breakup and non-elastic breakup. So non-elastic breakup is the dominant part in the alpha production. That is what is shown here. I'll summarize here. So this is the transfer cross sections which are measured for lithium-7, lithium-6 and beryllium-9, which are also showing some kind of universal behavior, and the early onset of transfer process is possible at much below the barrier. I will not go into this, so you can have a look at this. Today there is a talk by Prabhat Mishra, who is a student who will be giving the first coincidence measurement with boron 10 projectile. So we have not only restricted to lithium-7, lithium-6, 7 and beryllium-9. We have now gone up to the boron 10 also, which is also having the alpha clustering. So we are investigating this boron 10 coincidence measurements. So I'll skip these slides. So what he will show, you can attend this talk and listen to this. Okay, finally I'll come to the summary, and what are the observations from the weakly bound projectiles. We can see the complete fusion is suppression at above air energies. Then there is a large alpha production, mainly from the fragment capture and transfer. And there is a universal behavior is seen in all the plots like CF, ICF, alpha production, neutron transfer cross sections. The similar studies with RIBs, when the intensities are much more expected, then we can do the similar studies with the reductive ion beams, and the systematics can be extended further. This is the list of collaborators from my group, Nuclear Physics Division at DRC, from PAFR and University of Huelva in Spain. And also I would like to thank the Electron Linux staff for supplying very nice beams, and the data acquisition group, which is we are using the LAMP software, which is very fantastically working, and thanks to the group of the data acquisition as well. So with this, I thank you all of you.
Thank you, Vivek. Paper is open for discussion. So any questions? Yes.
The complete fusion suppression you have shown with ZP-ZT. At the lower value of ZP-ZT, it was not matching.
Yes. Yes.
You have not highlighted.
I'll comment on that. Yes. Yes. So this plot, if you see here, up to like these 2 points are like this is the 64 nickel. Okay. So here in this particular case, when you go to the lighter nuclei, it is very difficult to separate the complete fusion and incomplete fusion. So residue can be populated from the complete fusion as well as incomplete fusion. So whatever this published work, how they have identified these residues, it's not clear. Otherwise, it is typically when you see the all the heavy Z targets, it is showing same suppression for all the targets.
From 11th row.
Sir, it's not a nice talk. Sir, in a slide you saw the alpha band projection. So when
Yeah.
Yes. Yes. This one, when peak is down, then it again after 10 MeV, if the detector is very thin, then again it start peaking. So is there any clue why it is again start peaking in the left direction?
Okay, so here this is the bismuth target. So there may be contamination of carbon will be there, or oxygen will be there. It may be oxidized target. So you can see the lower energy part here. It is maybe the compound nuclear evaporation from that oxygen or from the carbon. So that we can neglect. So target is mainly bismuth target. It is showing the breakup bump here, which is typically 4/6 of the beam energy.
Thank you, sir. Cool.
Hello. Hi sir, thank you for this nice talk. So I have a question regarding that. Do you have done some experiment that where both the nuclei are weakly bound?
Both the nuclei, yes, we have done that.
So in that case, do you have found any such cross-section behavior where the inelastic cross-section is much larger than the elastic cross-section or not?
Okay, we have done the coincidence measurement recently with with beryllium 9 plus beryllium 9, and we have done the coincidence. So we could not do the inclusion measurement. If we do the inclusion measurement, we can be able to see the inelastic states. But anyway, from the coincidence measurement also we can able to get that inelastic band. We could be able to get that.
But the question is that why the inelastic cross-section is much larger than the elastic cross-section at unitarity limit or the breakup threshold point? Because I have found such discrepancy at that point.
Which system you have studied?
So in my case, I am not studying like any experiment. I am doing theoretical calculation for like two dimers is loosely bound to form a helium-4-like system, and another one is the trimer.
Typically, elastic cross-section is dominant reaction.
Exactly. We have found that elastic cross-section is much larger than the inelastic, but the enhancement in the inelastic channel is
No, but then you have to support it with experimental data. Theory, okay, one has to look into this inelastic part.
Thank you.
Okay, Santra.
Vivek, for your this 9 beryllium plus 144 samarium data that you have remeasured, there I think you need to renormalize on these calculations probably. If you want to like 0.7 you have multiplied and tried to fix the higher side.
Yes.
So
this
what
is
about
only-
lower side?
Correct,
Actually,
yes.
so there is a huge
Yeah,
discrepancy.
we have shown, we have marked as preliminary analysis. We are yet to finalize this graph. Yes.
Okay, yes. Okay. Thank you.
Okay. So we thank now Vivek for a nice talk. We move on to